In this video, I'm going to be talking about binding energy of a nucleus. It's part of topic 7 in the IB Physics Syllabus, so that means it's in common between SL and HL. So please read the success criteria of what I'm going to be talking about in this video. Okay, so let's start off by talking about this thing called the Unified Atomic Mass Unit, sometimes referred to as AMU. It's the mass of 1/12 of a carbon-12 nucleus. Now here's where I have to be really careful to point this out. It does say there nucleus, not atom, because the difference between the nucleus and atom would be 12 more electrons. We talk a lot about this because in this particular section of the course, we, as you can see down below, have 6 significant figures. Oops, sorry, that's 7 significant figures I've got written down below, 6 decimal places. And because of that, that will make a difference whether I said the word nucleus or atom. Now, in these terms, you can see that the mass of a proton, 1.007276 atomic mass units. That's very small. And for that reason, we tend to do a lot of calculations in atomic mass unit because it's a lot easier to deal with numbers like that compared to, if you look in your data booklet, the conversion between this would give me a times 10 to the minus 27 kilograms. It's a very small unit, but it makes our numbers a lot easier to deal with. This is also part of the nature of science, part of the course. Why would we come up with and use a non-metric unit? So those of you in chemistry will know where this came from. If you look at the periodic table and we look at carbon-12, we can then say 1 mole of carbon is going to be 12 grams. That's another part that we're going to be using later on in the course, where we're going to have to use, just like the chemist, Avogadro's number and a mole of a substance. So as I said, the proton mass, the neutron mass that I've got written there, you can find those in the data booklet. You can also then find how much they are in kilograms as well as atomic mass unit. And another unit that we're going to discuss later, mega electron volts, C to the negative 2. So here's what I want you to do first. Using the values in my table down below, I want you to calculate the mass of a helium nucleus. I have them here written in atomic mass units, and you can see I even have that conversion that's in our data table. 1 atomic mass unit is 1.6605 times 10 to the minus 27, a really small number, and it's really hard to tangibly figure out, how much is something compared to each other when I keep using scientific notation. Okay, so take a moment and do the calculation. Okay, so if you added the mass of the 2 protons and the 2 neutrons, you should get 4.03190 atomic mass units. But you can see in the chart that the helium nucleus actually isn't that much. Somehow I'm missing, and you can see my calculation, 0.03039 atomic mass units, or the equivalent of 5 times 10 to the minus 27 kilograms. Now, that might not seem like a lot, and you might say, oh, well, it's just small numbers. Well, no, it's real, and you're going to see it makes a very big difference. Okay, so where did this mass go? I mean, no poof Harry Potter magic is allowed in my classroom, and when people start to say things disappear, I go into panic mode. So the whole thing is, where did it go? Well, let's think about putting all those pieces together in making a nucleus. All those protons have to come really, really close together, but that should be a lot of repulsion. So it's going to take a lot of energy to move it all together. So that's where Einstein comes in. He said that mass and energy are 2 forms of the same thing, and we get this famous equation, E equals mc squared. Most people know the equation, but they have no idea what it actually refers to. So the energy will equal the mass defect times the speed of light squared. So that difference in mass between the actual mass of the constituents, or the nucleons separately, and the actual mass of the nucleus, we call the mass defect. And if I took those values from just one nucleus of helium and I put it into our equation E equals mc squared, that will end up giving us 4.54 times 10 to the minus 12 joules. Still doesn't seem like a lot, does it? I promise you, it makes a big difference. So let me introduce you to this term called binding energy. It's defined as the amount of work required to pull apart the constituents of a nucleus. So if I have a large binding energy, it's going to require a lot of work to pull it apart. Conversely, when I put all of those constituents, all those nucleons, particles in a nucleus, if I put them back together, the mass defect is going to be released in terms of energy. Now, I really need to point out, this is not the amount of energy holding the nucleons together. That's not going to be the case. So for example, if I had 40 joules of energy in total, if I took my mass and turned it into energy, and I put them together and 10 joules is released, there's still going to be energy in my nucleus. It's only 10 joules that would be the binding energy. It also means then, if I wanted to separate them all out, I'm going to have to use that 10 joules of energy in order to get back to my separate nucleons. So let's take a look. This was a definition from back in 2009. Binding energy can be defined as the energy released when the nucleides form from constituents, or the energy is required to separate a nucleus into its separate nucleons. I really want to point out one thing. In the November 2020 paper, you needed to be more specific than saying constituents. You could either say nucleons, or you could say protons and neutrons. Now that brings us to this graph. It's going to be one of the most important ones in this section on binding energy. Notice it says binding energy per nucleon, and that's because inside each different nucleus for each different element or each type of atom, the amount of energy needed to hold them together isn't all the same, and it has this very distinct property. We're going to talk about that more in our next video. For now, I want you to see that something small like hydrogen, and I have 2H there, that means deuterium. It's a proton and a neutron. It is a very low down there, and then you can see I have a peak where it says 4H, and that should be an E, not a C, for helium. There's a much greater binding energy per nucleon for that. Remember, that's an alpha particle. We then climb, or have a drop, and then we'll climb up to a peak. Some people say it's at iron 56, some people say it should be cobalt 56. The actual number, if you said either one of those would be fine. The idea though is we do have a peak at around that area, after which we've got a gradual, slow decrease in the binding energy per nucleon. And that's going to have an effect on how our nucleon will react in terms of fission and fusion. Okay, so I hope you have been able to now say yes to all these success criteria. Please take a moment again to read through what you should be able to talk about after watching this video.